So we will take now an example of the testing of the differential relays, and we have a different modules to test this kind of transformer protection application. So we have a wiring test, and we have a first trip to check the tripping time of the differential, and you can do also the backup test by using the ramping module, and stability test to check the stability against external fault using the Diff Configuration dedicated module. And number 5 is the characteristic test for checking the operating characteristic of the differential using the two ways, either by shot or by search. And we have a trip time test to check the tripping time of the differential function, which is supposed to be instantaneously. And number 7, the harmonic block or the harmonic restraint test for the second harmonic and the fifth harmonic. And we will take a demo of all of this in the practical demo board. So as you can see here, if you have a two-winding transformer, you can connect the first side, which is primary side, to the first current output, and the second side to the second current output, and you can get the feedback by trip 1 or trip 2 to the CMC binary input to test all this kind of protection function. And here is we have some example of the differential relay for the GEB643, and here is what we have one setting which we will use it in the practical demo board. So the frequency is 50 hertz, and here is the transformer data with the rated power and the high voltage side, rated voltage of the primary side, and the rated voltage of the secondary side or side 2, and also the rated voltage for side 3 or the tertiary voltage beside the vector group. And we have a CT ratios, and we have the differential characteristic setting, IDIF minimum, IDIF double greater, slope 1, slope 2, and the intersection point between slope 1 and slope 2, and last but not least, the harmonic restraint setting. So let us follow our Omicron Ohm's law. We have our Omicron Ohm's law, which starts with OHM, and so it's not like the general Ohm's law that we all know as electrical engineers. We have our own Ohm's law, as you can see. So the O stands for the test object, and H stands for the hardware configuration, and M stands for the test modules. And as you can see from this photo, it will be clear that the protection relay is our test object, and the CMC is our hardware configuration, which we will use to inject the current and voltage signals to the test object. And after that, we will get the feedback from the relay binary output to the CMC binary input to can test a different kind of protection functions. So we have here test object, we have hardware configuration, and test module represented in the test universe software. So it starts with the Omicron Ohm's law. So the test object, you have first to connect our PC to the CMC connected using the Ethernet port or the Wi-Fi port, USB type A or USB type B port as you can. And the second step is to connect your CMC to the protection relay. As you can see, side 1 is connected to the current output A, side 2 is connected to the current output B, and the trip relay binary output is connected to the CMC binary input to get the feedback from the protection relay. So starting from the test object, you can export the relay parameter setting using the relay software, which is S1 Agile in X-ray format. And after that, you can import inside the test universe PTT, which is protection testing template for any kind of protection relay, and you will get all of these values directly connected in the RIO file of the differential function to can be tested easily without any effort. Then we have here an example about the Riva B643 relay, and as you can see here is the transformer bias differential characteristic represented by between IDIF and I bias as a dual slope characteristic, and we have here IS1 is the minimum differential current, K1 is the slope 1, K2 is the slope 2, IS2 is the value of the I bias or the intersection point between the slope 1 and slope 2. And we have also the high set value, which can be represented in the relay parameter setting. And we will see how to test all this kind of parameters inside the test universe software. So the tripping characteristic for the Arriva B643 can we can take step by step. So we have some given parameters, which is slope 1 equal to 0.3, slope 2 equal to 0.7, and the intersection point is 4 as I bias per unit. And we have also IDiff minimum and IDiff double greater. So the resulting dual slope characteristic will be in that way. And if you need to draw it step by step, you can define the intersection point for each point, point 1, point 2, point 3, and you can define it inside the REU file of the differential function. And we can see this in the practical demo part 2, inshallah. So to represent this dual slope characteristic, we will have 3 points. As you can see, the point 1 is 0, 0, because the slope 1 is starting from the origin. So we can now check the point 2. The point 2, we have the given value of the I bias, which is the intersection between the intersection point between slope 1 and slope 2. So we can define the I differential value by using the equation, which is I diff equal slope multiplied by the I bias. So I diff equal 0.3 multiplied by 4, it will be 1.2. And 0.3 also, we have a value of the I diff, which is the unrestrained differential current, or the high set differential current, equal to 10 per unit. So by using the second slope equation, we can get the value of the I bias, which is equal to 16.57. But first, you can substitute in this equation to get the base point of the slope 2, which is 1.6. And after that, you can substitute by the I differential equal to 10 to get the I bias value equal to 16.57, as you can see from our calculation. So we will have the 0.100, 0.2 is 4, and 1.2. 0.3 is 16.57 and 10. So another example for the Siemens 7UT6, because it have a different given values. Slope 1 equal to 0.25, the slope 2 equal to 0.5, and the base point for slope 2 is 2.5. And we have for sure the IDiff minimum and IDiff double greater. So these points can be represented in the Siemens 7UT6. So the point 1 is 0, 0. The point 2, we didn't know the I bias and the I diff. And the point 3, we have the I differential double greater, which supposed 6 per unit. And we have we can check the I bias value using the slope 2 equation. So by using the line 1 and the line 2 equation, so you can get the I differential and the I bias for the point 2. As you can see, the I differential from slope 1 equal to the I differential from slope 2, because this intersection point, it locates on the slope 1 and also in the slope 2 in the same time. So we can get the I diff in this value, and by substitute in any equation of slope 1 and slope 2, you can get the bias value. So 0.2 will be 5 and 1.25. Then the point 3, by substitute the I diff double greater, which equal to 6 per unit, you can get the I bias, which is 14.5. So we have 0.1, 0.2, 0.3 for another example for Siemens 7UT6 relay. Then we will talk now about the hardware configuration, which is the second part. So if you have a 3-winding transformer, as we can see, we consist of primary and secondary and tertiary winding, and here you have the voltage rating for each side and the reference power for each side, along with the CT ratio for high and low and tertiary side. And you can connect one by one to the CMC to get the differential function. And as you can see here, we connecting the side 1 and the side 2 to the CMC binary output current output A and current output B, and we get the trip feedback to the CMC binary input. So now we can test the differential function between the primary and the secondary side. And by the same way, we can check the side 1 and side 3 differential protection function, as you can see in the attached photos, and many more tests to be done. And but please make sure if you are connecting the relay binary output in wet or dry. And the difference between wet contact or dry contact, the wet contact is have a potential differences, so it's called with potential. So if you are using a binary output from the protection relay which have a voltage drop across this contact, make sure to configure the binary input of the CMC to be a wet, and give him a threshold or the nominal value of the voltage drop across this contact. But if you are using a potential free or dry contact, which means spare or spare wired contact, make sure also to configure the right configuration in the test universe to get the right feedback. So about the third part, which is the test modules, as you can see, we have a different test modules to test the differential relay. So the differential software modules is suitable for 4 test modules. These 4 test modules can be used for testing the differential protection relays. So we have a specific test modules were developed to test a specific feature of the differential relay. All differential modules have a similar user interface and can be used easily as soon as handling any one of the modules have been learned. You can use this experience for all other 4 modules, and it consists of a lot of dedicated modules. One of them is the differential configuration test modules, which can serve for commissioning differential protection system or finding a configuration fault or wiring fault with this module. All faults which are located within the unit protection can be detected and corrected. And then we have a differential operating characteristic, the differential trip time characteristic, and also, last but not least, the differential harmonic restraint blocking. So starting with the tripping time characteristic, this differential trip time characteristic dedicated module can be used for check whether the tripping times of the differential protection are within the time tolerance band or not. So here is the maximum torque angle, as you can see. So the tripping zone will be encountered between the dual slope characteristic and the maximum torque angle, as you can see. And we will check this trip time by using the differential trip time dedicated modules. The second one we have, which is the operating differential operating characteristic test module, which is used to check the correct function of the operating characteristic of the differential protection. So it tests the relay's ability to differentiate between the faults within the protected zone and the fault outside this protected zone using the protection device tolerance. So this test modules offer 2 testing possibilities. The first one is the shot, and the second one is the surge. So speaking about the shot test, this test with a specific shots in the IDIF and IPIAS plan is used to verify the tolerance defined by the manufacturer. As you can see here, we can define some shots in the blocking zone and also can define some shots in the operating zone or tripping zone to check the how the relay differentiate between the blocking and the tripping zone. The second one, which we have in the operating characteristic with a surge. So the operating characteristic of the differential relay is tested by simulating fault inside and outside of the protected zones. So there are 2 test modules, as we explained, the shot and the surge. So now we will talk about the surge, which consists of several shots, for which the differential current IDIF is calculated at a specific biasing current using a bisection algorithm until the actual point of the characteristic is found. And you can see how it works in this. So it will define the nearest point of the differential, which will be suitable inside the tolerance band of the protection relay. As you can see, here is the way how to check the operating characteristic using the search test module. It will approach up and down until it gets the most accurate value of the IDIF, which should be within the tolerance band defined by the protection relay manual. So here is the harmonic block of the differential protection. It can be tested also using a dedicated test module called the differential harmonic restraint. So this test module is used for checking the correct relay behavior. So, speaking about the differential harmonic restraint test module, which is used for checking the correct relay behavior of the harmonic restraint of the differential protection. For example, it can be used in the inrush detection and the overfluxing or overexcitation relay function. And this test is aimed at checking the parameters of the harmonic restraint characteristic IXF and IDIF. And this test module over a two testing possibility: a shot test with a specific shot in the IDIF and IXF plan, and to verify the restraint and the trip area, and also the other way, which used the search test for the exact determination of the harmonic restraint characteristic percentage in the characteristic shape and the tolerance. So as you can see here, we can define some points in the blocking zone and the tripping zone to check the how the relay will react